Thank you. Okay, so well, hi everyone, and thanks well, of course, for the kind invitation to this seminar. I think it is always nice to talk, and especially in this diverse audience today, especially because actually the topic is quite interdisciplinary. So I think it contains a lot of different methodologies and other different approaches, and mainly over land, not much over ocean or water bodies. But I think the techniques can be actually interesting for you guys. So okay, you can tell from the title that I'm going to talk about physics and machine learning, and it almost looks like contradictory or even irreconcilable fields, right? Well, physics have traditionally relied on mostly mechanistic models to understand the systems, while machine learning is typically on the other side of the pendulum, right? And it typically only uses data, right? This is most of the common situation. No? Well, but after all, if you see the story, both Kepler and, if you allow me, Lecon observe instantations of a process that try to encapsulate this observational data or observations in general into a model. And this model should be able to explain what is going on. A model should be predict well in all cases. A model should be able to eventually extrapolate well to similar, well, even if a little bit different circumstances or scenarios. And it should be not falsifiable. Well, I started with neural networks like 20 years ago in my thesis, and then I jumped for different methodologies and approaches to another field, actually, to this field of remote sensing and geosciences. And I've been living 20 something years in the intersection or interplay between physics and machine learning. And it is more complex scenario, but I think, in my opinion, more interesting. Well, in this talk, I will try to convince you with a bunch of methodologies, both for relying on machine learning and deep learning in particular. And I will try to convince you that these techniques alone are not the solution for all the problems that we have in geosciences and the earth sciences in general. And in my opinion, that we need to take a little bit step back to think about the fundamental laws that we already know from physics or chemistry or biology processes on the system that we are observing and analyzing, and try to exploit this domain knowledge to encapsulate it in whatever machine learning model you want to develop. And in the hope that the model will be more consistent with our knowledge, more robust, eventually sparser, so simpler, and hopefully more interpretable. So, okay, let's start. But before starting, I would like to thank all the people that are and collaborators that we have here in Valencia, but also in other institutes and across the globe. I think without these brilliant minds, nothing about what I'm about to present will be possible. Okay, so let's start. Well, basically, it goes without saying that machine learning and deep learning, in particular, they're advancing many fields of sciences and engineering, and in particular of earth sciences. Well, and these techniques actually allow us to solve many challenging problems like classification and detection and regression, even visualization of complex data structures, etc. And advances are so many, and the applications are really so exciting that people have even advocated that AI, relying only on big data, fast computers, and scalable models, it's enough to solve whatever problem. And then, well, you can see these 4 covers of very important journals, publications that it has been even advocated that can replace at some extent both science and education, because you don't even need to worry too much about the understanding the problem or understanding the system that you are facing. And you can basically resort to data analysis, and you will be able to develop in reasonable times a decent model for prediction or forecasting or detection or whatever. Well, implicitly, I should say that a blind deep learning approach to whatever problem that you can encounter, well, okay, I could buy it, can do a good job. But yeah, but I think that this is yes, because in this rational, people is basically assuming that when enough data is observed, when there is no need to understand the physical principles, because the data itself acts as a prior belief or a regularizer, and data is a good and efficient regularizer. We know that. So the theory or the approach says, okay, with more data, better and more robust models will be achieved. And my question is that simple like that? As that? Well, the point is that if you look at the literature, you will see that the success of both machine learning and deep learning in general is not actually incidental. I mean, deep learning works very well in this kind of perfect storm where you have regularities in your data with strong autocorrelation functions, both, let's say, in spatial domain or temporal domain. So that's why you see a lot of advances in video or image and speech processing, for example. And actually, this is the same situation that we are observing in the earth sciences. Also, the second point why this technology this technology is actually very successful is that well, you have to have access to big data, and it should be readily accessible. And you also have to have access to huge computational resources, which is the case right now, and also fast and very scalable models, right? And last but not least, if you look at the literature of applications of deep learning, let's say, in 99% of the applications, users and practitioners, they only care about, well, developing a machine learning model that should be developed automatically, ideally, right? So in not paying too much attention to the details of the model development, and not even taking too much effort into the understanding what are the particular drivers and processes. So practitioners just want to reach high accuracy levels with a minimum effort, and if possible, automatically, right? And that's really a problem. And I do not buy this way of doing things, because well, I highlighted there in red like three main concerns I have. Well, these are the main problems that we have. Not understanding much. High precision is the only goal, and we do not care too much about the problem. So I think that this has been given a lot of troubles to a lot of in a lot of fields of application. And my point here is that, well, we need to develop models that should be kind of respecting physics at some point. We should be caring about developing models that should be kind of interpretable. This way we could understand processes and the systems itself by data analysis. And of course, the models do not, so far, they don't get the notions of space or time or not even causal relations, right? So these are like very important concerns that and not only myself, there are many people working in this domain, and this is where I'm gonna be talking a little bit on this talk. Okay, so this is the outline of the presentation. Basically, I will present you like a bunch of methods in these three fields of interest, I think, for the earth sciences and machine learning. So I will briefly talk about different methods for explainable AI, also some methods and methodologies for physics-aware machine learning, and a little bit on causality too. Well, by the way, you can see this logo here, and I guess you know this parable of the blind man who have never come across an elephant before, and who just want to learn and conceptualize what an elephant is just by basically touching it, right? And each blind man only feels like a different part of the elephant body, but only one part. And the moral of this parable is that we humans, or let's say machine learners, have the tendency to claim that the absolute truth just by basically looking at a very limited amount of data and only a part of the problem, not an holistic way. No? So we are kind of biased to our subjective experience, and we tend to ignore all people's limited subjective experiences, which maybe eventually could be equally true to the one that we are proposing, right? So something similar, I feel, is happening in the earth sciences nowadays. So no real scientific advance through the machine learning pipeline, right? Well, you have the ingredients, you have the models, you have the domain knowledge, but there is this lack of interaction between these two worlds, no? So this is the menu for today. Let's jump on it. I will start with explainable AI or interpretable machine learning. And you can see here, like, well, this is our basic assumption. So it's a very simplistic one. So we are assuming that X is causing Y, and we want to derive a predictive model, F, that basically predicts well Y from X. And F can be a big, fat neural network or a random forest or whatever, no? And the thing is, what feature relations and what feature representation did the model actually learn to do well in the prediction phase? No, this is the main question that we want to answer here. And does this model actually make sense? How can we assess this? No, and this is like the field of explainable AI. So the main question here is, how do we interrogate models, machine learning models? No, and there are like many different approaches. Well, not many, maybe there are hundreds of different methods. And here I basically put this table in which you can see that there are like basically 4 families of methodologies. One is mostly based on the traditional sensitivity analysis. Another one is more towards decomposition of the model itself in pieces, so each one should be kind of interpretable. Another one is based on what we know as distillation. So let's try to replace this big neural network with something simpler and eventually more interpretable. And then the 4th family of methodologies for OceaniX is basically more interested in visualizing what is going on inside the neural network, right? So visualizing the basis functions that the network learned. So, okay, I will give you like a bunch of examples for each one of them, and yeah, but then we can clarify whatever you want, right? So, okay, let's start with sensitivity analysis. So probably this is the most standard way to understand what a model has learned, and it is basically about deriving a ranking of the features by, for instance, perturbating one of the input variables and then looking at how the error changes in the output. And then you just rank that. You know? This typically works for all machine learning models, so it is not intrinsic to whatever. But I should say that, for instance, in kernel methods, it's very nice because you have the sensitivity analysis formulas are analytic. So essentially, they come in closed form solutions. So once that the model is trained, you take the weights, you apply the formula, and you get the ranking for free. So you don't have to do this eventually quite costly perturbation analysis or whatever sensitivity analysis you want to perform. And this, we have shown that in that paper for Gaussian processes, for emulation of radiative transfer models, super vector machines for classification of droughts, or yeah, even for kernel methods that try to measure or estimate dependencies, nonlinear relationships of association between multivariate data sets. Well, this is essentially a very kind of a naive way of gaining knowledge through the model itself. But this is, so far, is looking at the model from outside, right? Well, here I'm putting a particular example that we have been working in the last weeks. Well, this is a neural network architecture to detect droughts. So for that, we typically use several input spatial temporal cubes or variables, so moisture, temperature, GPP, etc. And we want to, well, to encapsulate that in a representative feature representation. And in this case, we use an autoencoder. But we want the system to be autonomous, to be unsupervised. So we don't want to provide labels for that. No? So we take this feature representation in the latent representation, and then we fed it to Gaussianization flows. So, and we take the maximum log likelihood or the log likelihood of this representation as a kind of anomaly score for the detection of droughts. And you can tell from the figures on the bottom that, well, you can see that the model captures quite well this Russian heat wave of 2010 between May and June, July, something like that. And it can actually provide you with decent and reasonable maps of drought detection. But well, this was a very severe, very dramatic drought, actually, with many casualties and many crop losses, etc. And the good thing is that the network can learn through space and time, and then derive these detection maps in an unsupervised manner. But more interesting than that is to learn what the network learned, right? So in this case, we apply a method called integrated gradients, and this is able to identify both in space and time, and for each one of the variables, when and how do they activate in order to eventually detect the droughts nicely, right? For example, here we see that of course during the drought period, most of the variables that the network ingests, they activate, readily activate, right? Like, but it is also important that during the fall, this happened over springtime or summertime. During the fall of the previous year, some other variables like Trapper lie or liver index or the soil moisture, they were kind of combined, and they were like precursors of this drought. So that can give us some hints and some ideas on what are the variables important for the network to detect in an unsupervised way these severe droughts. Okay, let's jump to the second type of models for interpretable machine learning. This is the family of model decomposition, and this is quite an alternative to develop a very complex model. So in this case, you want to constrain in a way the class of functions of the model that you want to run. And in this case, we use Gaussian processes because, well, basically the information that the structure of the model is encapsulated in the kernel function itself, and it is obviously interpretable. In this case, for example, we combine a linear kernel, on a Gaussian kernel, and a noise term. This was used for estimating crop yield in the US Corn Belt from different time series, and vegetation indices, and vegetation optical depth, and soil moisture time series, temperature, etc. And the point is that after training, again, the GP returns like an automatic sensitivity analysis feature ranking, a predictive mean and a predictive variance, but also an estimation of the noise variance, which was really important too in this particular case. And also you have this trade-off between linear versus nonlinear effects, and that can tell you something about anomalies too. And the models themselves, the model parameters, sorry, themselves, they actually encapsulate what is the notion of regularity and anomalousness of the point. In our case, the points were counties. So you could identify in space and time which was the variable that was rising like an anomaly of crop production and for what particular county. Well, the third family has to do with model distillation. So the idea here is quite simple and interesting. So the point is that while current machine learning models are typically very huge, over-parameterized black boxes, and it is really interesting to develop models that kind of mimic those in a similar way to surrogate modeling or emulation. No? So you try to generate like I don't know, a simpler decision tree, a random forest, or even a linear model that tries to mimic the complex one. So this way you can learn something out of this, and because it is readily interpretable, right? Instead of developing these surrogate models, one can learn these alternative feature representations. So there are other more complicated distillation processes or distillation models as well. And they are interpretable, but not explicitly interpretable, but in some metric space. And also, well, there are some works nowadays that they try to do this model distillation with more complex networks, trying to impose some sparsity or sparse promoting regularizers as well. But so far, I haven't seen too many developments in the field of earth sciences. But maybe it would be nice to explore this area farther. And the fourth thing, the fourth family of methods for interpretability have to do with looking inside the neural network, right? So looking at what the basis functions are, how do they differ, what is the redundancy of the filters, etc. And this is really complicated, and it is really challenging to assign or to attribute a particular feature to a particular process, because it is a very complicated architecture. Well, there are approaches that kind of simplify this task. For instance, this RAM, the regression activation map, I think, yeah. And in this case, basically it tries to summarize this method, the relevance of the activations in the inner layers to do obviously the output prediction. On the right-hand side here of this slide, you may see a deep network that was trained to predict the crop yield in the Indian wheat belt here. And the RAM told us that which were the specific times and scales that were really important to do so, at least in the eyes of the network. Okay, so far so good. Let's take a look at this other field. The second topic in the presentation has to do with physics aware, let's say, or sometimes it is called, or it is named, you will find it in the literature as physics guided or physics informed, many different ways. No? Okay, so far the model that one can achieve is typically accurate, and you can scrutinize it from outside, or even taking a look at the basis functions inside and see what is going on, and maybe eventually crossing fingers, you can learn something out of this feature ranking and feature representations. But what we actually want to do here is not only to take into consideration the observational data, but also all our domain knowledge into the model development itself. So this is the field, right? So we are incorporating the domain knowledge eventually in the form of particular equations inside the model itself. So you can learn both in principle the parameters of the network and the parameters of the ODE/PDE all together and end-to-end. That would be a particular approach for physics-aware machine learning. No? Well, why there is so much interest into this right now? Well, the point is that the truth is actually that we need to live in this interplay, because models without the data are pure fantasy and essentially it's just a prior belief. And data without models are kind of chaos, because they run the risk of overfitting. You do not actually guide the model, and you're missing some important pieces of the domain knowledge that we already have for centuries. No, so in recent years you can see that there is a high interest in combining both this data-driven machine learning with physics laws and constraints. And the gains are multiple. Typically, one poses and one finds in the literature that the motivation is only for consistency, but sometimes it is also for sufficiency, for understanding, for speed as well, right? So because very often you will find physics-aware machine learning tends to be sparser, because in the end you are just exploring a subspace of the solutions that you could eventually explore with an arbitrary machine learning model, learning from data alone. Okay, in this survey paper on the bottom, we basically explore like different families of different methodologies for living in this intersection between machine learning and physics, if you allow me to name it like that. In here, well, I'm basically identified like 4 different groups of techniques. So how to blend or combine data models, how to emulate or do surrogate modeling of physics models, how to learn parametrizations through both observational data and the forward model, and the last point, I would say, in which machine learning and physics intersect, is about learning equations, converting equations out of data. Okay, learning physics. No? So I will give you a good bunch of examples for each one of them. So for the first one is, I think this is the standard one, the most traditional one, is based on something that in machine learning we know quite well, which is the constraint optimization framework. Well, here several formulations for classification and regression are possible, and this is the standard approach. The idea here is just to include an extra regularization term that minimizes not only the error, but the sum of all impossible solutions, guided, of course, by a physical model. In this example, in the figure on the left here, the author just wanted to estimate the temperature at different depths in a lake. And then they managed to impose the known relationship between temperature and density. And they managed to include this regularizer, penalizing the smoothness across the different layers in the lakes. No? So by minimizing not only the error, but also these inconsistencies, you could, well, they claim that you could achieve even better results in terms of MSE. Okay, a second example. This second example tries to put us in the case where very often happens that you have observational data, but you also have a model that you can trust, and then you want to combine them all, right? Both. So in this case, we basically develop a Gaussian process that takes these two sources of information and combines them in the kernel function itself. So essentially, one kernel function is dedicated to observational data coming from satellite observations, and the other to the RTM simulations, to the radiative transfer model simulations. So the model learned the relative relevance of these two pieces of information, and also learn how to compensate the lack of one in particular regions with the wealth of the other of the simulations, because you could actually fill in the space of the whole range, right? So we applied this to parameter retrieval of leaf area index, a critical parameter in the land observations, and for that we use Landsat observational data. For consistency, we run simulations with an RTM called Rosale. And we run it for different regions, and once that you have these data sets, the GP learns how to combine them. And what it is nice is that it can achieve a little bit better confidence in the out of region. Inside the region where you have enough data, they perform roughly the same as a standard GP. But outside, you're kind of constraining the variability, and the uncertainty is more constrained and more trustable in a way. You know? Okay, the third method that I would like to introduce you is called convolution processes. This is, again, a sort of a Gaussian process treatment, so a Bayesian treatment, and it has like the structure very similar. You can tell from the figure on the left, very similar to a kind of a neural network, right? So you have different multiple outputs, and then you want to do this, you want to design this kind of process, a GP, in a way that incorporates some knowledge about the system that generated the data, of the generating mechanism. So if you know something about, for instance, the ODE, you can derive the particular equations that that they translate into a particular kernel function. So this is a quite powerful algorithm, and since very often we have access to these ODEs or even PDEs, you can in principle generate these convolution processes and learn from data, and at the same time learn something about the equations themselves, the parameters of the equation, and also being a probabilistic treatment, you will derive confidence intervals for the prediction and automatic ranking of the features. So in this case, for instance, we were interested in fusing different information from different sensors, from different satellite sensors, to estimate soil moisture. And for that, we encoded the relationship between the soil moisture and the precipitation. But we are not using precipitation at all. And what it was really cool in this method is of course can import. Well, sorry, here you can see here in the on the right, you can see that the predictions of the different time series are quite accurate. Also, it can import information from one sensor to fill in the gaps of another sensor, even a non-existent sensor at that period in time. But it was not only about accuracy. Of course, you can apply it, and then it runs quite nicely and predicts soil moisture for different sensors. And what it was really interesting is to look at the latent forces that the GP learned. And in this case, it was quite striking that the latent forces were related to precipitation. So by encoding this ODE, the latent force that it was governing the system was precipitation, because you were implicitly telling the algorithm, okay, you are predicting soil moisture, you have to do it well there, but you know that soil moisture is mainly driven by precipitation, but I'm not going to give you that. I'm just going to give you the general first order ODE. I mean, it was a very simple thing. You know? The point is that once that you have trained the GP, this latent force GP, you learn not only the latent forces that in this case were very related to precipitation, as you can tell from the figure, but also you learn like the time decay, the attenuation, eventually the damping parameters, etc. No? So you learn something about the dynamics of the soil moisture process. No? Well, this is one of the interesting methods that could be applied in other contexts. No? Okay, of course, the fourth methodology has to do with emulating complex codes with machine learning. And this has been like very useful in practice in many different areas. No? This is called either emulation or surrogate modeling. So basically, you want to replace these algorithms, these models with a machine learning model. It can be a deep neural network, a random forest, or whatever. No? But I would like to emphasize here that this has been typically pushed because of for the sake of speed only. Because once that the machine learning model is trained, you can essentially run very fast, no? With the simulations. But I would like to emphasize also that you gain something else. If you replace the RTM with a GP, you will also have predictive variance for free. You will also have confidence intervals, and you will also have ranking of features for free, right? On top of speed. Okay, so the fifth approach, we typically call it hybrid modeling or hybrid deep learning. And in this case, this field is kind of becoming more and more mature, even though that it is still in its infancy. You know? And we have recently reviewed in this perspective paper the role and challenges of deep learning, no? And how the integration of deep learning with the process understanding can make a difference. No? So on the left-hand side here, you see a general framework to, let's say, physicize, if you allow me, a deep learning model by basically including constraints in the network layers itself, not as an extra regularization term as before. No? On the right-hand side, you see an example of a deep learning model that can learn, let's say, these motion fields in an accurate manner, but at the same time, there is incorporated in one of the last layers a working function that comes from a model, and essentially tries to deform or tries to make the predictions of the network physically consistent with the model. No? So works this solution of the motion field, and then what it is nice in these architectures, thanks to this field of automatic differentiation, and you can basically learn both the model parameters and the deep network parameters end-to-end. Okay, and one example for the last box of this of this methodological or taxonomy of interplay physics and machine learning, you have this discovery of ODEs or PDEs from data. Well, this is quite interesting and quite even, I would say, even more challenging than causality itself, no? Because you're learning something that you don't even have an expression for, no? So this has to do with learning differential equations from data. Also, this has many implications on Earth and climate sciences. And once that the model is trained, in principle, there is no need to solve costly equations or codes, right? So in this example on the left, well, the authors basically they say, okay, I'm interested in learning a pre-computed basis consisting of all model data of all data interactions for all the monomials, let's say x times y, x times y squared, the differential of x times the differential of y, etc., and so forth. And then you treat that as a regression problem. So essentially, you put this basis function, then you have the data, and then you impose a sparsity, so you get rid of the irrelevant monomials, let's say in this expansion, and then you can learn this equation itself. No? So the model is very simple, and it has found some application in earth sciences, but still it's quite sensitive to noise and the dimensionality. And actually, you do not know, you cannot control the amount of bases that you will need. So it's a very powerful idea, but it has to be like kind of domesticated for a particular method, right? Or a problem, sorry. So in this case, for instance, we use it for well, trying to learn the equations governing the biosphere. So for that, we collected 12 biospheric indices summarizing the state of the ecosystem. So you may imagine evapotranspiration, soil moisture, GDP, NDVI, etc. Gridded in space and 8 days in time for 10 to 12 years, something like that. Then we extracted some principal components, and then we applied the method to learn which was the relationship. I mean, the differential equation governing this dynamics of the system. So we basically identified this. We passed through this bottleneck of PCA because we identified that the PCA1, let's say, summarizes the vegetation productivity. The PC2 is more related to water availability. So we could say something about what was the semantic meaning of PC1 and PC2. But anyway, you could run it in principle with the original raw data, but the differential equation could turn to be like very complicated to scrutinize, to analyze. So we run the algorithm, we get some stable results and robust results with a decent correlation coefficient, and then we could identify the differential equation governing this pair of semantic PCs. Well, once that you have equations, you can do a lot of things, right? You can study stability or bifurcations or tipping points, so you can actually characterize your system, right? So that's the holy grail of learning from data. No? Okay, and the last example I would like to mention is related to parametrizations. So this is a very important topic and problem in earth sciences. So very often we don't know which is the a priori distribution of in our parameter space, but we have two things, two very nice ingredients. We have a decent model for the forward pass, let's say, for generating or for encoding the radiative transfer of energy from the parameter space to the observation space. And then you have data, you have observations, right? So in this work, what we learned this parametrization densities for a particular RTM transfer model. So the model basically gives a Gaussian likelihood and assumes a Gaussian prior, and we want to fit these prior parameters. The problem here is that the models, the RTM models, they are very complicated, and if you put it in inside let's say the equation of the Gaussian mean, that's really tough though, because it's really hard to operate with that. But this can be solved actually with variational inference. So we introduced the variational posterior into the log marginal likelihood. Then we chose the variational posterior to be Gaussian. That's an assumption with well, with a mean and a covariance that in the end you can learn with a neural network. And since the Kullback-Leibler divergence here between two Gaussians is easy to compute on the right with respect to parameters, you can compute the expected value of the log likelihood. Well, we compared to other sampling schemes and to other approaches like Monte Carlo, etc. And it was quite nice, quite robust, but it is very limited in the eyes of high dimensional spaces, a lot of examples, etc. Right? So yeah, more work is needed here to make the learning of the distributions nicer and more robust. Okay, and I think I'm not sure if I have more time, but I would like to say some words about this, about understanding is more important than fitting. What happens if you don't want to develop a model in the end, even a physics-guided model? What if you just have data and observations and you want to learn the causal relations between them, right? So this is of course, the field of causal inference, of causal discovery, and it is quite important in general, but also for in the case of Earth and climate sciences. And it is important in our case, for three main reasons, or three main applications. First, for testing hypotheses. Second, to compare models and data. So this way you could basically you could come up with a decision, okay, this model resembles more the data or the observations in a causal sense, not just in a correlation sense or association sense. And the third point is because that would allow us to assess the causes of extreme impacts as well. No? So of course, you can think of many different applications to learn how the system works. And this is basically what we summarized in this paper, basically with, we expose the kind of mathematical background with the theories of causality. This is quite solidified now, but it has a lot of problems when working with time series, and in particular with the challenges that our system is imposing on us, right? Teleconnections, missing data, non-stationarities, non-linearities in the wild, missing data, etc. So multivariate data that they are not coincident in space or time. So there are many challenges that one will have to face in the future of causal discovery from observational data in the earth sciences. No? Essentially here, we were also proposing like a family of four main families of methods. And well, I prepared some slides and maybe I can skip that so not to make it too long. And we can, well, I will go through them very quickly. One of the families is based on Granger causality. So here what we did is to extend that to the nonlinear case with Gaussian processes. And in this case, you can incorporate different components in the kernel function itself that account for nonlinearity or trends or seasonality or non-stationary processes. So getting rid of the constraints or the problems that the vanilla Granger causality has. And it could actually identify like more clearly in a sharper way non-spurious causal relationships between El Nino and soil moisture, for example. A second, oops, something happened here. Oops, yeah. The second case or the second family is based on convergent cross mapping. So it is a methodology based on more on manifold learning, and essentially here. This is an alternative approach to the previous one. It is based on state space reconstruction, and it has been used for some problems in the earth sciences and geosciences. And essentially here, one decides that X causes Y if you can recover the manifold structure of Y from the manifold structure of X. Intuitively meaning that X created some sort of information footprint in Y. So it goes in the reverse direction to Granger causality indeed. The method is very sensitive to noise though, and we try to address that with a combination of two different causal methods and also by bootstrapping both space and time. So we could come up with more robust identifications. So we apply to, again, big data sets of accounting for many different physical processes here. And we're, of course, working on the land. And we apply it to these three variables, GPP, air temperature, and soil moisture, and we could derive like explicit, especially explicit maps of causal impacts between or across the different variables. So, and the maps could kind of make sense. So in dry or water limited areas, GPP is caused or driven by soil moisture. Temperature is mainly an effect mainly in the northern boreal regions, and soil moisture in boreal regions actually matches with a reduction in radiation and temperature. So the maths can kind of make sense. The third family goes straight to the point. So it basically tries to test the conditional independence between two variables. So independence between X and Y given Z. And for that, of course, you need a test of conditional independence. And that can be really, really hard in multivariate data. And for that, for instance, you could, I don't know, you could use partial correlation, but it has been also argued that this could be replaced with a Gaussian process, for instance. So you could replace that. So you could account for nonlinear, let's say, measures of dependency instead of just correlation, even conditional correlation. So these can cope with nonlinearities. Actually, it has been recently proposed a method based on this particular approach in order to compare models with observational data, right? So you have observations, you have different models, and then you can derive through PCA or varimax, you can derive modes of variability. And each mode of variability, it has associated a time series, which in the end is a node in a causal graph. And then you do not compare spatial temporal cubes directly, but you compare models, and you compare models to observations through the causal graphs that you can learn individually from each one of them, right? So you basically account for how many nodes are coincident, which are the missing links, the spurious links, direct links. So you can come up with a summarizing statistic to compare models to observations. And finally, what happens if time is not involved, right? So maybe you have causal problems in which not necessarily time is the mediator, is the governing processes of the causal relationship, but you don't have time involved in a particular case, no? So what happens in that case? Well, from a pure statistical point of view, this is a very challenging point because the joint PXY can be actually factorized in two different ways, and both are valid, no? The problem here is really, really challenging, and for that there are a bunch of methods that can deal with that, can cope with that. And in this approach, for instance, this is called the structural causal models, you can actually assume, let's say, that the potential cause should be independent of the generating mechanism of the function translating X into Y, let's say, assuming that X is the cause. Yeah, and you have a generating mechanism that basically transforms X into Y. So the Y should be, or the prediction of Y should be as independent of the potential cause as possible. So this is a very, very simple and very nice instantiation of a model for running with this. And imagine that you have the cities in the world, and you have like their altitude and the temperature, and you want to, time is in principle not involved here. So you plot one versus the other, and you can fit temperature from altitude or vice versa, no? And both are valid regression models. So then what you do in second step is to test for the independence between the residuals and the assumed cost. So in this case, you will see my mouse. So in this, essentially, you will basically compute the dependency between the residuals of predicting temperature from altitude and the potential cost, which is altitude. Okay, and you can see that the residuals are more independent. While here, if you do the other way around, if you plot the residuals of the altitude with respect to potential cost, temperature, you can see structure, right? And the dependency measure is much higher than on the other case. And then you can argue that it is altitude causing temperature. So this is the right causal direction, right? Not the other way around. So we try that with a good bunch of problems in geosciences where we have a ground truth. So we know what's the cause and what is the effect. So this way you can run the algorithm and then evaluate how good it is. And the good thing is that the results were not that bad. We're better than just rolling a dice, and results were kind of good in this problems in geosciences. So there is hope when time is not involved and only working in the bivariate case, only two variables involved. Of course, there are many assumptions under these approaches, and there are many other possibilities to come up with alternative methods. No? And finally, I would like just to promote this platform that we are building. So in this platform, it's a platform for causal discovery and causal analysis. So essentially here, so far, you can do very limited things. So essentially, you can download the time series with ground truth. Then you run your causal discovery method at home, upload your solution, and the system evaluates how good you are, how good your method is. No? And it returns like a ranking of the main methods for the most successful ones for the different problems. So you can learn something, right? Which method is more appropriate for dealing with your data. Okay. So that was it. Basically, I would like just to say some final words. And for that, I will use like the 3 standard sentences or mottos that you'll find in statistics, right? So the first one is, you can be right for the wrong reasons, okay? Yeah, completely agree. But in order to resolve this, embrace causality. The second one is a quite standard too, no? All models are wrong, some are useful, right? Yeah, fine, too. But then care about make these models plausible and consistent. So essentially trying to incorporate your domain knowledge in the system, in the model building. And third one is AI is not deep learning, man. And that's also very important. So in order to do a real advance on AI, actual AI, we should be more concerned not just in fitting, but in trying to understand through data analysis, explainability, abstraction, understanding, causality come into play. And all three, if you look at these three issues, all three, they advocate for a more interaction between the domain experts and the machine learning or computer scientists. So education is going to be the key word here, I think, in the near future. We have summarized some of these ideas in this agenda that you can find in this archive link. That was it. Thank you very much for your attention.